In this video, we will be looking at capacitors in parallel. In the previous video, we have seen capacitors in series. If you see that video and come back to this, then it will be easier to grasp this concept. So when two capacitors are connected in parallel means they will be connected like this. Two capacitors are connected like this, and in turn they are connected to a potential difference V. V means this will be at V potential, this will be at 0 potential. So the difference across this battery is V volt. See, this point and this point are in connection with this. There is no device here, so electric device is here, hence this will be at V potential, this will be at V potential. Since this is 0, this point and this point will be at 0 potential. That means, suppose if it is a capacitor of capacitance C1, the potential drop across this capacitance is V, and then the potential drop across this capacitance is also V, irrespective of whether, like, if its capacitance is C1, its capacitance is C2. Irrespective of the value of the capacitances, because of the way it is connected, by virtue of the connection, the potential drop across this capacitance and this capacitance will be equal, and that is equal to V. When capacitors are connected in series, all the capacitors will have equal charge. And when three capacitors are connected in series, the charge on each capacitor will be Q. They are same. When capacitors are connected in parallel, then potential drop across each of the capacitor will be the same. Then for the first capacitor, this is C1 and this is V. We know that for any capacitor, C will be equal to the ratio of Q by V. Then for this capacitor, Q will be equal to C1V. The capacitance or charge on the second capacitance will be equal to C2 into V. C1, C2 are different, V are same, then Q1, Q2 must be different. So actually what happens, the charges that came out of this source may be Q, that is distributed in the first and second capacitors. Hence, the total charge pushed away from the battery is Q, then the charges developed across each of the capacitance is Q1, Q2, then Q must be equal to Q1 plus Q2. Then from this, what is Q1? C1V. What is Q2? C2V. So what we are here trying to find, as in the previous case, is that you are going to replace these two capacitors with a single capacitor. Then in that case, same battery you will use, but in place of two capacitors you will be using a single capacitor. You don't know what its value is, let me call it CP, capacitance, effective capacitance value in parallel. So across the potential difference, same potential difference V. So the total charge these two capacitors together drew was Q, then this single capacitance must be drawing the same charge Q. Then from this relation, you know that Q will be equal to CP into V. If you substitute this Q here, CP into V, we will be getting what? CP will be equal to C1 plus C2. So the total capacitance or the effective capacitance in series will be what? Sum of the capacitors. If this is 10, this is 1, total capacitance will be 11. So like what we said in the previous case, effective capacitance when the capacitors are connected in parallel will be greater than the greatest. Suppose you have 100, 20 and 30, three capacitors. What is the effective? 100 plus 20 plus 30. So it becomes 150. So the effective capacitance when the capacitors are connected in parallel will be greater than the greatest value of the capacitors connected in series. So these two things you will have to remember. In series connection, capacitance, the reciprocal of the effective capacitance, or you can say that 1 by C1 plus 1 by C2 plus and so on. In general, you can write effective capacitance in series will be 1 by C1 plus 1 by C2 plus n number of capacitors whole power minus 1. When they are connected in parallel, this can also be written as C parallel. Effective capacitance will be in parallel will be sum of all the capacitors connected in parallel.